Welcome back. I would like to discuss about controllability and observability. Of course, over the YouTube or internet, you can find more formal definitions about controllability and observability. Here, I will focus on how I use them in my daily control systems life. Okay. So if you have watched this video, we are trying to make some matrices Hurwitz by finding gain k. Actually, if you watch this video, this gain k is k1, okay? Or if you are designing a Lowenberger observer to estimate the states of the system, we are trying to make this matrix Hurwitz. So if you are watching this video without watching this, I will suggest that you watch this first to make sure that we have a full understanding of this video, and then you watch this video. Basically, right, in controls, we would like to make some matrices Hurwitz, like A minus BK or A minus LC. And I would like to talk about dual notions of controllability and observability. Basically, how I use them in my daily life is that given x dot equals to ax plus bu and y equals to cx, I know that if ab is called controllable, then I can place or I can set the eigenvalues of a minus bk by choosing an appropriate k to anywhere I want. Of course, anywhere I want with respect to the stability or making it Hurwitz is I would like to choose their real parts less than 0, right? So I can, in other words, if AB is controllable, then I can always make this Hurwitz. And for making it Hurwitz, I can use basically Paul eigenvalue placement. I have a video and then MATLAB example video on this, or optimal linear quadratic control. I also have a video and its example, MATLAB example video on these two topics. Basically, I either use pole placement or optimal control to make A minus B or this A minus BK Hurwitz. That was number one. Similarly, if A and C, the pair AC is observable, then I can always find L to make A minus LC Hurwitz by using pole eigenvalue placement or optimal control. For this reason, in most of the papers, if not all, if you are dealing with a system, the common assumption is that the pair AB is controllable and pair AC is observable. All right, so this is how I use observability and controllability and observability in my research. So let's look at the formal how we can ensure a system is controllable or observable. All right, so given two matrices A and B, n by n, n by m, let's look at this controllability matrix. Basically, you form this controllability matrix, the system order is n. So the first entry vector or matrix, depending on the B, is you put B, then you put A multiplied by B, A2 multiplied by B, all the way n minus 1 power multiplied by B. So if rank of this controllability matrix is n, meaning that basically you have n linearly independent rows of columns of this matrix. If you don't want to count linearly independent rows or columns, basically just compute this determinant of gamma multiplied by gamma transpose. It should be not equal to 0. In MATLAB, how you do this, basically after you compose this controllability matrix, go to the MATLAB, write gamma prime, which is the transpose, right? If it is non-zero, then that's perfect. Then the pair AB is controllable. Let's do an example. I picked an arbitrary AB matrix. Since we don't deal with the y equals to cx, it is not here, right? Controllability only looks at A and B. So we have this A matrix, we have this B matrix. In this case, this is 2 by 2. So we need to go n minus 1, which basically our controllability matrix will be just this portion. If you put B, comma, A multiplied by B, I just multiplied AB here in MATLAB. So you obtain this matrix. So from this structure, it is very clear that it is rows are linearly independent of each other, or columns are linearly independent of each other. So the rank is then 2. Again, if you are having difficulty in understanding, I am sure you shouldn't, what do we mean by linearly independent, right? For example, if you have 1, 0, 1, 0, in this case, or let me give you another example, 1, minus 1, minus 1, 1, you take this row multiplied by minus 1, you produce this other row. So in this case, these rows are linearly independent. So rank of this matrix is 1, not 2. But this is not the case here. So we have rank of gamma controllable matrix is 2. If you don't want to do that, go to the MATLAB, write determinant gamma gamma transpose. You are going to obtain this number, which is non-zero. Then we say A and B, the pair AB, is controllable. That's perfect. Then you can go here, that you can always find again K to place your eigenvalues anywhere you want on the left half plane, or you can use optimal linear quadratic control. All right, so you may ask, right, this question. This video is, again, what I mostly use in my daily control systems life. Let's say for a reason that rank of gamma is not 2 here. Then the system is not controllable, and the stuff that you can do with your system will be limited. In this case, by designing control gain K, you may not be able to change all the eigenvalues of your system as desired. And in this case, we would like to do controllable decomposition to assess what eigenvalues of the system I can change and what eigenvalues of the system I cannot change. If the eigenvalues of the system that I cannot change are on the left half plane, then we say the system is not controllable but stabilizable. Meaning that, I can change some of the eigenvalues, and the remaining eigenvalues that I cannot change are already on the left half plane, so that I can still make A minus BK Hurwitz. So, but right, to understand this, you need to do control decomposition. So you really need to understand the eigenvalues that you cannot change, basically, needs to be on the left half plane. But again, if you want me to do a video about controllable decomposition, please let me know. Most of the systems that I dealt with are either controllable or stabilizable. Honestly, I will say controllable. If the system is not controllable, you can include more actuators to your system to control the motion of the system in a controllable manner, such that the pair AB will be controllable. So for this reason, since I most of the time deal with controllable systems, I just wanted to directly link it to, basically first, given a system like this, I will check if the system is AB is controllable, and most of the time it is controllable. Then I jump into pole placement or optimal control to make A minus BK Hurwitz. Again, if you want me to do a video about control decomposition to dive more into details about controllability, let me know. All right. I am jumping now to the observability. Again, almost most of the systems that I dealt with are observable. And given a pair A and C, basically we construct this observability matrix. Once again, order N. We start this time with C, CA, and all the way up to C multiplied by AN minus 1. And basically, if rank of this omega is n, still we are counting linearly independent rows or columns. And if you don't want to do this count, go to the MATLAB, just write determinant gamma omega transpose multiply omega, it should be non-zero. After you form this observability matrix and find non-zero determinant, then you say the pair AC is observable. Perfect. And If it is, then linking back to here, then you can always find L by using pole placement method or optimal linear quadratic control to make A minus LC Hurwitz. So, all right. So again, I am considering the same example, but just I added this C matrix. In this case, we are computing this omega observability matrix. This is basically the C itself, and this is C multiplied by A. In this case, you can directly see the rows or columns are linearly independent, meaning that if you take this row multiplied by some number, you cannot produce here this second row. If you don't want to do this, go to the MATLAB, write determinant gamma transpose gamma. It is 2 non-zero, then AC is observable. Similar to the controllability case, there may be cases, although very rare, system may not be observable. In this case, if the system is detectable, meaning that the eigenvalues of basically A that you cannot change through L are on the left half plane, you can still make A minus LC Hurwitz, since the eigenvalues that you cannot change are already on the left half plane, and the remaining eigenvalues either on the left half plane or the right half plane you can change. This is kind of a similar to the controllability case. In this case, this is a sensor placement case. You need to include more sensors to see to make the system observable, and to assess which eigenvalues that you cannot change, or whether the eigenvalues that you cannot change are on the left half plane or on the right half plane. You perform basically observable decomposition. So similar to my comment on controllable decomposition, if you want me to dive into more in detail about basically controllability and observability, likewise stabilizability and detectability, and what happens if you don't have a controllable system or an observable system, then you need to perform control decomposition and observable decomposition. That will give you an idea about whether the eigenvalues that you cannot change are on the left half plane or not. But I would like to make this video simple, and as a professor, I dealt with a lot of systems, and most of the time engineers introduce sufficient number of sensors to make C bigger and sufficient number of actuators to make B bigger, and most of the systems that I dealt with has an A, B that are controllable and observable. Again, I first check this, right? So before I try to make this Hurwitz, I check if these matrices are controllable, observable. Then once I see that they are controllable and observable, then I can design K and L to make these Hurwitzes. So most of the time, I assure you, in engineering systems, AB will be controllable and AC will be observable. But again, sorry for repetition, if you want me to dive more into the technical details and theory behind controllability and observability, as well as controllable decomposition and observable decomposition, let me know. I will be happy to do that.